Okay, we're to functional groups. A functional group, as I explained, is a group of atoms attached to the carbon backbone. So it's a group of atoms that have been covalently bonded together, attached to a carbon backbone, and they behave the same way no matter what carbon backbone they attach to. The groups we will discuss are the hydroxyl, the carbonyl, the carboxyl, the amino, sulfhydryl, phosphate, and methyl. We won't discuss them in great detail, but just a little bit for you to be cognizant of them. Okay. Right here is a structural formula, let's say for carbohydrates. Okay. There are two forms for carbohydrates. Carbohydrates exist in a linear form sometimes, in three-dimensional, or a cyclical form. Most of the time they like the cyclical form because it's more energetically favorable, but they move between two forms. All right, we go first to the hydroxyl group. The hydroxyl group is an OH. This line here is where this bond would be where it's attached to the carbon backbone, as you can see here. It imparts a slight amount of polarity. If you recall, go back, study the previous inorganic, polar covalent, non-polar covalent. Because oxygen is more highly electronegative than hydrogen, but not enough to actually steal the electron, then it will pull the electrons around the oxygen more than the hydrogen. Because the electrons will travel around the oxygen more, that area will be more negative compared to that. So it imparts a certain degree of polarity. Now, if you go back, remember I told you that water dissolves things that show polarity. Why? Because water is charged. Water is charged, so by having this hydroxyl group, it gives a little bit of polarity, gives a little bit of dissolvable. Here is alcohol. Alcohol, for example, has that. Its polars result of electrons spending more time near the electronegative oxygen. So you can kind of see, can form with water molecules. So you can kind of look at this. Okay, going further. The carbonyl group, I'm not going to say much on it. It has to do more with positioning. It has to do with positioning, whether it becomes something called a aldehyde or a ketone. I'm not going to say much on that until we actually need it, but that is another functional group. Okay, the carboxyl group is that's where the term, a contracted term, is a combination of a carbonyl and a hydroxyl, carboxyl. It also imparts a significant amount of polarity, because you got this here and you got these oxygens. The other thing, though, is these two oxygens get together in a way, I'll say it like that, and can steal the hydrogen electrons. When the hydrogen's electrons are stolen, it kicks this off. Now, go back to your old stuff, because hydrogen gets kicked off, then this can act as an acid. Because remember what an acid was, a proton donor. Remember what an acid was. So two things the carboxyl group can do. One, to give a certain amount of polarity, and also, if wherever it is, it can act generally in an acidic manner. Like acetic acid. Okay? The amino group. The amino group is an NHH. Now, this is a situation where this guy would like to take on another hydrogen. I don't know if you recall, I mentioned that in order for an atom to be happy, it needed to fill its outer shell, but still be stable in three-dimensional space. This guy would like to pick up an extra to kind of give it more of a symmetry, shall I say, more of a symmetry. Now, what will happen is, if it picks up an extra hydrogen, then it would act as a proton acceptor. It would act as a proton acceptor. Plus, it would give a certain amount of charge, too. But because it would act as a proton acceptor, it could also act as a base. So the amino group in acid-base could act as a base because it would try to accept another hydrogen. But it also gives a certain amount of polarity, as you can see. So So again, that's another group. Okay? And I'm going to be bringing those back up later as we actually put them in play. Here's the subhydro group. Again, I'm not going to say much about this. Subhydro groups generally like to bond to themselves to form something called a disulfide bridge. Okay? Where this will come up is kind of in the skin. Okay? Disulfide bridges are heavily present in proteins. Heavily present in proteins. The subhydro group, then the more subhydro groups, the more the disulfide bridges. The more the disulfide bridges, the tougher the protein. The more the disulfide bridges, the tougher the protein. And in order to get the disulfide bridges, you have to have a lot of subhydro groups. So when we get into the skin chapter, I'm going to say it to you like this. Hair is a form of skin, and nails are a form of skin. Hair is tougher than skin because it has more subhydro that can form disulfide bridges. That's what makes it harder than skin. That's why if someone was to put a hot something to hair, you would have that sulfur smell. Now, nails are stronger than hair, and because they even have more sulfur, subhydro groups, than hair does. So I'll be bringing this up again. Cysteine is a major component of your skin, your hair, and your nails. All right. The phosphate group is another group. The phosphate group would start out where it would be hydrogens here. The phosphate group, which would be more of a phosphoric acid, can kick off hydrogens, but they leave their electrons. So wherever there's a phosphate group is heavily charged. And also because it can kick off some hydrogens, it can sometimes act in an acidic way. That's what we call it. And you'll see this come back up, known as the phosphate group. The methyl group, I'm not going to really say much. It has to do with the position, and we'll talk about that perhaps when we talk about DNA, but I'm not going to say much on that. So here's kind of, you can go through. Don't get real heavy on it. Don't get real heavy. I know this is a lot. So, but just kind of keep it in mind because I will be bringing it back up as time goes on. All right. So those are your functional groups. Now I'll just mention nomenclature. Nomenclature is how you name organic compounds. This would be one of the first things that you would do in an organic chemistry course. But this is not an organic chemistry course. This is a biology course. But anyway, there are special ways based upon how many carbons are bonded together, whether they have a double bond or a single bond, and so forth like that. So like this is propane, these is propene because it has the double bond. I won't get into it a lot. You just have to accept it because you would have had to know some organic chemistry. To say, here's another thing that you'll have to just accept. The carbons have a special numbering pattern. What happens like with this, you pick the longest chain. So it's several rules that come up in organic chemistry, and this would be taught at the beginning of an organic chemistry course. But since this is not, you just have to kind of accept what numbering, if I need to use numbering, there is. Again, I'm just familiarizing so you can see where I'm coming from on this particular aspect. Here again is numbering, as you can see, based upon the linear and the cyclical. You've all heard, I'm sure, that are healthy, and so forth, omega-3 fatty acids, for example. And so the fatty acid we'll talk about on the lipid thing, but that omega, they number the carbons, and, in Greek alphabet, alpha is the first letter and omega is the end. So when you say an omega-3 fatty acid, you're looking at the fatty acid and you're saying, where is the first double bond from the very end? Where is the first double bond from the very end? In this case, 1, 2, 3. That would be the third. So I just wanted to kind of show you that when they say an omega, some of those, linoleic, linolytic, and always eat good omega, 3 fat, where that omega term is coming from. Now, speaking of something else in this is something called an isomer. Always remember in Latin, Iso means same. Iso means same. So they're molecules with the same molecular formula, but a change in the structural formula. The same molecular formula, which is the one that has the numbers, the proper numbers, but the arrangement in space. For example, you could take some item that you have, let's say a microphone, or let's say whatever you have, melt it down, lose no pieces of the plastic, and make an airplane out of it. So think of it the same way in chemistry. You would have the same numbers of atoms, but you rearrange them differently. By rearranging it, then everything changes, because chemistry, molecules, just like the big world, are based on shape. They're based on shape. So in this case, C6H12O6, which was the formula we said for glucose, hey, is also the formula for fructose and galactose. It's just that the atoms are arranged differently in the molecule on 3D. So when you look at isomers, there are different types of isomers. We have structural isomers, geometric, and optical. I'm not going to get very heavy. A structural isomer basically is like this. It's a change in the arrangement of the atom. So here's pentane. Here's the same number in a different deal. Okay. A geometric isomer requires that you have carbons that have a double bond. Double bond is harder to bend around. So in this case, two constituents are on the same side, two atoms on the same side. That's called the cis form, whatever these are. This here, they're on opposite. This is what we call the trans form. So this is what we call, it's what we call cis-trans isomerism. I'm sure you've heard, about these trans fatty acids, that these trans fatty acids are not good for you. That's where this comes from. It's the arrangement of how you have these atoms in space on the fatty acids. We'll chat on that again. So cis-trans isomerism, okay? Here's a transoleic acid, and here's a cis. Yeah, it's kind of bent, and it has to do with the double bond area, okay? So we go further, okay? Optical isomers are basically kind of a weird thing. It's how the molecule rotates polarized light. Now, polarized light is one direction. Light in the ceiling is coming down in multiple areas. But we have a device called a polarimeter that can send light in one direction. And what you basically do is put the molecule in there, the sample, and you turn a dial. If you turn the dial in order to see the light come through. So there's a light on one end, the molecule, and your eyeball. And what happens is you turn the dial to see when you can see the light come through. And the light, the turn of the dial, arranges the molecule in the right direction for light to travel through, this polarized light. So if you have to turn the dial to the right, it's called the D form. The dextrorotatory, that means right. If you have to turn it to the left, it's levorotatory. So it has to do with this thing to have an asymmetric carbon. I'm not going to get into all of that, but I am going to get here real quickly. And that is, let's take glucose. Glucose has an asymmetric carbon, so it can rotate polarized light, a requirement to have optical isomerism. One form of glucose called D-glucose, you can rotate to the right. Then you have another form called L-glucose that rotates to the left. Now, just like with anything I mentioned, shape is important. D-glucose is called dextrose. That's the sugar stuff. That's what we even put in IVs. And you can digest it and everything. L-glucose, on the other hand, cannot be metabolized. It actually will go through the intestines undigested and can actually act as a laxative. So just by, you have both a glucose, but the arrangement of the atoms will determine if it's a D form or an L form. And you can kind of look at, here's L-glucose, which is sweet, but nothing like, it's almost bitter, nothing like D-glucose. So I'll close here and we'll start carbohydrates next.